Hello, this is our pre-lab discussion for Module 3 in CHY 114. Today we are looking at nitrate analysis. If we just pause for a moment to remember where we are at, we are continuing with our Green River project, investigating the water quality issues that we have found along this river. In Module 1, when we looked at TSS and turbidity, we were taking a look at the amount of solids suspended in the river, the amount of actual suspended solids, and how that affected the clarity of the water. In Module 2, we went on to look at the amount of charged particles. We studied the conductivity that was in the river, and we looked at the acidity levels when we looked at the levels of hydrogen ions. Today, with the nitrate analysis, we're now shifting our attention to another very specific ion, where we're looking at the amount of nitrates in the river. Remember that nitrate is one of our polyatomic ions with a formula of NO3, and it has a -1 charge. Nitrates are particularly important because nitrates are typically one of the limiting nutrients in an aquatic system that, when there is an excess amount, can lead to some algae blooms, which is precisely one of the problems that we are seeing at Site C in the Green River. In very extreme cases, these algae blooms can lead to huge dead zones within water bodies. And we see a good example of that in the Gulf of Mexico. A staggering amount of rivers and water bodies in general. Sorry. It probably comes as no surprise, end up funneling into the Mississippi River. And we have all that farmland in the Midwest and just sort of all this land in general that then gets funneled down into here and dumps into the Gulf of Mexico. Along the way, picking up lots and lots and lots of different nutrients. And we end up with this huge dead zone within the Gulf of Mexico that pops up at certain times of year when things are filtering in. And so that's an extreme case. It's certainly not what we're seeing here, but it is a result of things like nitrates and how they can then filter into a water body. And so that's of concern for us. And so we want to investigate what might be going on with our nitrate levels in the Green River. When we look at where nitrates might be coming from, housing development at Site A is certainly a potential spot. Nitrates are a huge component of fertilizers. And in any new housing development, there's a lot of various fertilization going on, especially with new lawns. And so we could very easily have some runoff coming from there entering into the river. The textile mill might directly be discharging nitric acid, possibly right into the river. And the formula for nitric acid is HNO3. Nitric acid is one of our strong acids, meaning it will completely dissociate into H+ and NO3-. And so there's a possible source of nitrates. And just generally, acid rain, one of the acids that are possibly present in acid rain is nitric acid. And so we might just have some natural acid rain deposition happening, which could lead to some nitrate levels. And so that's why we're taking a look at this today and seeing what role nitrates might be playing in the quality issues that we're seeing along the Green River. In order to study nitrate levels, we're going to use a very common technique that is used throughout chemistry and really throughout science in general. We're going to use spectrophotometry. In a way, spectrophotometry is similar to turbidity when we measure that, in that the measurements rely on looking at the amount of light that passes through a sample. But with spectrophotometry, we're going to get much more detailed with that. We're going to see that we use only very specific wavelengths of light, which we'll talk about, as opposed to turbidity just measures sort of the amount of all of visible light that's passing through. So we're going to get very specific with our wavelength. And we're also going to take advantage of some laws that correlate to what we call absorbance, which we'll talk about in a second, to the amount of matter that we have in our sample, our concentration. And so if we think about light passing through a sample, we have our light source here, and the amount of light that is, we set as sort of the I initial. And so it's just the amount of incident light coming from our light source. passes through our sample. Now, it probably makes sense that not all of that light is going to pass through the sample. And so then we're able to detect the amount of light that does actually make its way through. And using that, and this is not something that we'll have to calculate, this is all done internally with the software, but using that, we can then calculate what we call the transmittance, capital T, which is simply a ratio of those two numbers. It's a ratio of how much light is actually seen versus how much light actually passed through. And so if only half of the light actually makes it through, then we get a transmittance of 50%, and so on. When we're looking at spectrophotometry, though, when we're using spectrophotometry, what we really want to use, because of the relationships that we'll talk about, we really want to use absorbance. And so rather than thinking in terms of the amount of light that passes through, we want to think of how much light didn't make it through, how much was actually absorbed by our sample. And so absorbance is just a function of transmittance. You take the negative log of the transmittance, and that provides us with an absorbance value. So again, how much of the actual light that came from our light source, how much of that light is absorbed by our sample that it's passing through. The absorbance is then a key factor in what we call Beer's law, or sometimes called the Beer-Lambert law, in which the absorbance is equal to this Greek letter epsilon times BC. And we'll talk about what all these mean in just a minute. But this is a very useful law for us. It's a very useful law in science and in experimentation in general, because it's used for lots of different types of measurements, just like we're going to see today. Very, very useful law. So when we look at all of these different values, A, again, is just our absorbance. So that's how much of our light is absorbed by our sample. And that is unitless because it is based on just a ratio. Epsilon is what we call the molar absorptivity coefficient, sometimes called the molar extinction coefficient or just extinction coefficient. And that is a physical property. The molar absorptivity is a physical property of whatever substance it is that we're actually looking at. B is the path length of the cuvette, and that is typically 1 centimeter. So it's set usually at 1 centimeter. The cuvettes typically are 1 centimeter, partly just to make this calculation easy. And so being 1, it really doesn't end up factoring into the math of this calculation of Beer's law. C is our concentration, and typically in units of molarity when we're working directly with the Beer's law equation itself. Now, this should just make sense if we just sort of think about the nature of this equation in general. We see that as concentration increases, absorbance increases. Let's come back to here, and that should just make sense, right? If we have higher concentrations of our sample, there's more stuff in this cuvette, more light is going to be absorbed as it passes through. That's something that again, should really just make intuitive sense. And we do, in fact, see that from the equation, that as concentration goes up, absorbance is going to go up. Now, we could rewrite this. Let's say we wanted to find the concentration of some unknown. So we have some unknown sample of nitrates, perhaps, and we want to know what the concentration of those nitrates are. We can rewrite our Beer's law equation to solve for concentration. So we would just simply divide both sides by the molar absorptivity coefficient and by the path length, and we would get C equals A over epsilon times B. And so we can find the concentration that way if the epsilon value is known. If we know the molar absorptivity coefficient, then we can simply measure the absorbance, plug it in here, and we're able to find the concentration. Beer's law is sometimes used in this way. If the molar absorptivity coefficient of a particular substance is directly known, then we can do this. We can run it in this way. Oftentimes it's not known precisely enough for our purposes, though, or there are other factors which make it a little bit more difficult to analyze concentration in this way. The other thing that we can sort of take home from Beer's law, the other thing that Beer's law tells us, and we already alluded to this a little bit, is that this really means that absorbance is directly proportional to concentration. If we don't even think about the molar absorptivity coefficient, we don't even think about the path length, we can see just from the equation, just like we were talking about, that as as concentration increases, so does absorbance. And so there's a direct mathematical relationship there. And so if we can simply define that relationship, that specific relationship for our system, if we can define that relationship between absorbance and concentration, then there's no need to know epsilon. And we're going to see what that's all about right now by looking at what we call standard curves. Standard curves make use of Beer's law in that what we do is we can take known concentrations of our compound of interest, in this case, nitrates. And so we're going to take known concentration of nitrates, and we're going to actually establish that relationship between absorbance and concentration. Now, make note here that when you are creating a standard curve graph, they must be in the form of absorbance versus concentration. And remember that that's in the form of y versus x. And so absorbance must always be on your y-axis, and concentration must always be on your x-axis. Remember, back to graphing fundamentals, that's your dependent versus your independent variables. And so what we are going to do then is we're going to measure the absorbance of some of these known nitrate concentrations, and we're going to graph those and establish that relationship. And so here we have just the table of just an example table. This is directly from your pre-lab, where we have some known concentrations of nitrate. And so we just have these concentrations that were made up from a sample. So we know what these concentrations are, and we're measuring the absorbance of those particular samples. So that's all we're doing. We have these known concentrations of nitrates, and we're measuring the absorbance of those. What we're going to do then is just create a graph of those. Now, again, you can use any spreadsheet program that you want in order to make this graph, but let's just look at how we do that and look at a couple of graphing fundamentals as we're doing it. It's a good time right now is a great time to talk about some of the graphing fundamentals that we might not have talked about in detail yet. Oop, you can see I've already got my graph there. There it goes. And so here we have that same data. And so this is our nitrate concentration versus our absorbance. Right now, I'm just making a graph in Google Sheets. And so again, this is the same exact data as we had right here, our nitrate concentration and our absorbance. There's our nitrate concentration and our absorbance. You can see that I've labeled my headings. Always a good idea in your spreadsheet to label your data. And you'll also note that, remember why I said, this is, again, just some graphing notes. I said that we're going to want absorbance on our y-axis and concentration on our x-axis. One thing to note about Google Sheets and Excel both is that if you graph in the way that we show you, if you make your graphs by selecting your data and then inserting your graph, the first column is going to be your x-axis. The second column is going to be your y-axis. And so keep that in mind when you're setting up your spreadsheets, that it's just much easier to set them up how you're eventually going to want your graphs. And so we've done that here. We want our concentration along our x-axis, our absorbance along our y-axis. And so then we can simply select our data range, insert chart. Maybe there we go. And we can see that a couple things we see. One is that Google Sheets tends to be a little bit more intuitive sometimes, and it automatically selected scatter chart for us because Google Sheets saw that we had these two different data sets that it looked like we wanted to compare. And so it chose scatter chart for us, which is good because that's what we want. What we're going to ultimately need from this, though, is our trend lines. So we want to just click on our data points, and then we're going to click on trend line. So now we've got our trend line there. But what's really going to be important for us, or a couple things that'll be important, is we want our equation. Our equation is going to be what we're really after here. So our label, we're going to use our equation. So there's the equation of our line. We're also very typically concerned with our R squared value. And I'll talk more about the R squared value in just a few minutes. And so here is the graph of our absorbance versus our nitrate concentration. And so we've established our relationship then between absorbance and concentration for nitrates. And we have the equation of that line here. Let's just take a look at what this would look like in Excel. Again, same exact idea. So here I have my nitrate concentration, my absorbance values. I'm just going to select my data range, insert charts. With Excel, I'm actually going to choose the XY scatter. So there's my scatter plot. And you can see that Excel just doesn't give you as many options right to start out with. And so we're going to have to add our axis labels and things like that so we can have our proper graph. But I'm first going to, there we go, select my actual graph. I'm going to right click, add trend line. So there's my trend line. I'm going to display my equation on the chart and display my R squared value. Now, keep in mind with Excel, you do have other options such as being able to move your equation, and I'd recommend doing that. Just move it to someplace where it's easier to see. Another thing that might be handy for you, or it might make things a little easier, is you can actually change the font. And so I would do that. Just blow that font size up a little bit, make it easy to see. Since we want this to be a proper graph with everything that a graph needs, we need to add in some axis labels. And so we're going to add in our axis titles. Remember that we're in Excel, and depending on what version of Excel you use, these might look a little bit different. Or we're going to add in our horizontal and our vertical labels. Then we just need to click in here so that we can actually change our axis labels. So absorbance on our y-axis, nitrate concentration with our units as ppm on our x-axis. And we can move our equation a little bit here. Oh, there we go. Whoa, what did I do there? There we go. And we just need a proper title. Absorbance as a function of nitrate concentration. And there we go. We have our equation for that and our R squared values. Let's just talk about the R squared values for a minute. Because we know that absorbance and concentration are directly proportional to each other. That we know that from Beer's law. As absorbance goes up, concentration goes up. And so ideally, if these measurements were all taken perfectly, if our concentrations, if our solutions were made up exactly perfectly, and if our absorbance values were dead on accurate, then since this is a direct correlation, these two are directly correlated, our R squared value would ideally be 1. Now, this is the real world, though, and we know that there's going to be a little bit of flux, so to speak, in our absorbance values. Our concentrations and our solutions probably are not made perfectly. And so the R squared value just gives us an idea, essentially, for how good our measurements really are. 0.9875, pretty good. And we can say that, and we can see, in fact, that most of our points pretty much lay on our line. And so that's good. That's what we want to look for. If you have an R squared value that is quite a bit less than 1, and if you can, in fact, see the point difference. So let's say, for instance, maybe this point was this absorbance value was 0.363. Now we can see we've got an R squared value of 0.92. Not a very good R squared value for the purposes of standard curves. And this isn't a hard and fast rule, but just something to maybe keep in the back of your heads, that if you're starting for standard curves, if you're starting to get R squared values that are below 0.96, 0.95, somewhere around there, then you might want to start thinking about your measurements. And in fact, we can see that one right here. And we can see that these 4 pretty much lay on our line, but this point's way below. Tells us something probably went wrong with this measurement. If you made the solutions yourselves, that might tell you that something's wrong with that solution. And so you want to go back and try to maybe remake that solution. Or perhaps your absorbance value was off. And so remeasure the absorbance of that particular solution. And so let's say we do that here. Let's say we get this graph and we look at that third point and say, yeah, I really don't like that. Something might have happened there. Maybe there was a smudge on the glassware. Maybe you put it in incorrectly. Something happened. And so you remeasure that one, put it back in, remeasure it, and you get a value now, again, of the 0.856, and it gives us an R-squared value that we're happy with. And so that's just something to keep in mind as you're creating your curves. Because it's easy enough, especially in our lab setups, you can be creating this curve during the experiment. There's no reason for you to necessarily wait until you get home to run this part of the analysis. Do this as you go. Set up Excel on your computer, set up a Google Sheet on your computers as you're working, as you're taking these measurements, and plot this as you go. You don't need to necessarily insert, when you're doing that, all of the labels and the title. That has to be part of your final product that you turn in. If you want, during lab, just set up the actual points and get your R-squared values so you can see what that looks like. Let you know if you maybe have to retake a measurement before you even leave lab. So it just gives you a way to see how good your data is before you leave. So that's how we're going to graph these. And so again, our goal is to come up with this relationship. So we now have our established relationship between absorbance and nitrate concentration. We know what the equation is relating the two of those things together. So let's take a deeper look at that equation. So here's the equation that we came up with right here. 0.1485x plus 0.026. Again, that's just coming from our trend line right here. 0.1485x plus 0.026. So that's the equation for our line. That's our equation that establishes the relationship that we're looking for. Now what we want to remember, though, is what y and x actually are. Remember that y was our absorbance value. So let's put that right in for the y value. So we have absorbance equals 0.1485 times, remember, x is our nitrate concentration. So let's put that right in here. And then plus our B value, so to speak, our 0.026. And so absorbance equals 0.1485 times nitrate concentration plus 0.026. And now we just use a little bit of basic algebra, a little bit of basic math to solve for our nitrate concentration, because that's ultimately what we want. Remember, our goal here is to be able to take absorbance measurements of our unknown. And I haven't really talked about that yet, but that's our goal, is to be able to take absorbance measurements of our unknowns. In this case, our 5 sample spots. Take absorbance measurements of those and convert those over into concentration of nitrate. And this equation now gives us the power to do that. We rewrite this equation to solve for our nitrate concentrations. We can then take an absorbance value of one of our Green River samples and plug that right in. We're going to take that absorbance value, subtract 0.026, and then divide that total by 0.1485. That gives us our nitrate concentrations. And it's important to remember this. It gives us our nitrate concentration in ppm, because that's what the concentrations were. Those were the concentration units from our standard curve. We measured concentration in ppm for this. And so we plug in that unknown absorbance value, or that we plug in the absorbance value of that unknown, and we're going to get a nitrate concentration. And here's just an example of that. So here's the equation that we just had. So we were just working with this equation here. And in this particular example, we take an unknown, and we get an absorbance reading of 0.739. So we're just going to plug in that 0.739 for the absorbance. And here it is here. We do the math of this, and we find a value of 4.80 ppm. Simple as that. And that's the basic experiment that we're doing today. Or that's the basic analysis that we're doing. Is you first have to find the absorbance values of some known nitrate concentrations, and those are all prepared for you. Not necessarily these exact concentrations. There'll be different ones that you're going to use, but it's spelled out right in the lab manual and the concentrations are right on the bottles that you're going to be using. So make sure that you're always looking at the labels on your samples. But you're going to measure the absorbance values of some known concentrations of nitrates. You're going to create this graph so that you can then establish your relationship between absorbance and nitrate concentration, so that you can then develop your own equation based on your results, your own equation that relates nitrate concentration to absorbance. You will then find the absorbance values of the Green River sample sites, plug those absorbance values in here, and find your nitrate concentrations. And so let's just talk about some of the logistics here a little bit. And so, as I mentioned earlier, absorbance is a function of transmittance. And so they're really just sort of the flip side of the same thing. How much light is transmitting through our sample? And so where transmittance is a ratio of the light that's transmitted through the sample relative to the amount of light transmitted through a blank being just water. And so the first thing that we have to do is show the detector what it looks like when all of the light transmits through. And so in other words, we have to set what we call the I0. And so that, if we remember back to here, there it is, I found it. So first we just have to tell the software what this value here is, this I0. And so we have to set this initial transmittance. And so that's just some logistical stuff that we have to do. And that's when you look in your lab manual, the section in your methods called calibrating the spectrophotometer. That's what this part is all about, is basically just showing the software what it looks like when all of the light passes through. When there's nothing there to absorb, that means this amount of light is hitting the detector. And so you're just using a blank for that, using some distilled water. Again, just simply, all you're doing now is you're showing the spectrophotometer. This is what it looks like when all of the light passes through. And so that's called calibrating the spectrophotometer. We also have to deal with the fact that only certain wavelengths of light are going to be absorbed by our sample. We're not going to get into a lot of detail with this aspect of absorbance right now, because later on in lecture, in a few weeks, we're going to be studying electron arrangements in much more detail than we have so far. So far, when we've talked about atomic structure, all we've really said is we have our protons and our neutrons in our nucleus, and our electrons are somewhere on the outside. It turns out, and again, we'll be studying this in exhausting detail in lecture, but the electrons are not simply scattered about haphazardly around the outside of the nucleus. They are arranged in very specific energy levels, quite often called Bohr shells. And so because of this, and we can see a depiction of that here. Here's our nucleus, and here are some very specific energy levels where electrons can be found. And so this means that electrons, for instance, would not be found right here where my cursor is, or they would not be found right here. You're only going to find electrons on these very specific energy levels. In some ways, you can think of it as the rungs of a ladder. You can stand on each of the rungs. You can't stand between a rung, or between two rungs, right? Same thing here. You can find electrons on these energy levels, on these shells, but you can't find them in between. Again, there's tons more detail there, and this definitely doesn't tell the whole picture. We will be getting into that detail later on in a few weeks in lecture. But for us, what we need to know for now is that means that only certain amounts of energy can actually be absorbed. Specific energy levels translate to specific wavelengths of light. Again, we'll be talking in more detail later about the electromagnetic spectrum. For now, you can think of wavelengths as things like different colors are actually different wavelengths of light. The visible light that we see and interact with are different wavelengths as compared to ultraviolet light. And so we have these different wavelengths which correspond to these different energy levels. And so what we need to do, because not all compounds absorb all wavelengths, they don't all absorb all energy levels. And so we need to actually tell the spectrophotometer what wavelength of light we want to measure the absorbance at. And so that's really the next big part of your methods section, where it says in your methods, determine lambda max. What we're doing in determining our lambda max is telling the spectrophotometer what wavelength we have to use. We do run into another small issue when it comes to nitrates, as it turns out nitrates don't absorb light at all in the range that we need for the spectrophotometer. And so we can get around that. First, what we do is we use cadmium to reduce our nitrates to nitrites. So we're going to reduce them to NO2 minus. This is already done in the samples. You don't have to do any of that. Just know that it is done. So we've already reduced our nitrates down. We can then complex the nitrites with a coloring agent. That coloring agent definitely does absorb at about 543 nanometers. So now we have something that will absorb. And you'll actually see this. This is part of what you're going to do. You're going to do this for all of your standard curve solutions, as well as all of your Green River samples, is we're going to add in this coloring agent so that you can then, so we then have a colored system, a colored sample that will absorb within the wavelength range that we need it to. Keep in mind, after you do that, just procedurally, you have to wait at least 10 minutes after adding your coloring agent. I think it talks about this in the manual. It definitely talks about your time frame. But this is the first thing that I would do pretty much, is get all your samples ready and add your coloring agents. So get those all in so that so that your time has started. You can then go through the calibrating the spectrophotometer and getting ready to go. Maybe get your spreadsheet set up so that you're all ready to record your actual concentrations and absorbance values. You'll get all ready to go while you're waiting for those 10 minutes. But then after that 10 minutes has gone by, a couple things. One, I would definitely note in your notebooks any visual observations you make. Can you actually see a color difference between samples 1 and 2, something like that? But now we have to tell the software what wavelength we're going to use. Now, your lab manual does walk you through this, but just to sort of note a couple things, steps 1 through 4 in the determining lambda max section, those are all about establishing that proper wavelength. And so just keep that in mind as you are, and these pictures are taken directly from the lab manual. But when you are in that portion of your methods, when you're in the determining lambda max portion of your methods, if you don't see curves that look something like this, with a definite peak here in this range, or a curve that looks something like this on a different page in there, you've done something wrong if you don't see curves like this. And so go back and probably just start again with that part of your procedure, because you do have to see these curves here. And then what you're doing again in that procedure is choosing the proper wavelength. There's a couple ways that you can do that. And this will be a little bit easier to see when it's in front of you, when you've got the program up and running. But you can either click directly on the wavelength here, or you've got some checkboxes over here. And again, whatever one you choose should be right around 543. It might not be exactly 543, and that's fine, but it should definitely be within that range. If you're choosing something that's around 250, then something's gone wrong. And that might happen. You might see, for instance, that when you're looking at this spectra when you're doing this part of the procedure, this part of the peak might actually be higher over here, and the software might choose that because it's a higher peak. But you don't want that one. You want to make sure you're choosing something that's right around right around that 543 range. So make sure that you're choosing something around there. But then once you have that, so at this point, you've got the spectrophotometer all ready to go. Again, sort of remembering how LoggerPro is set up, just like the other measurements that we've taken using that software. At this point, absorbance should be popping up down in the lower left-hand corner of your screen. And so now you can just put your samples right in and directly measure the absorbance and then get all the data that you need. And so hopefully this has been helpful. You should be able to basically get to lab and get right to a lot of it. There are some pre-lab activities which would help you through walking through how you're going to do a lot of this analysis. And so maybe watching this video is helpful with those. Certainly some of the graphing you might have to do of this video hopefully was helpful. And so that is it for our module 3. Good luck, and I hope everybody has success with this lab.